who's going to talk about on the coming down from infinity of soft coalescing Brownian motions.
Okay, thank you for everyone to having me here, and I apologize a little for changing the title of my talk a little bit. So the title now is about the soft coalescing Brownian motion, not the local time coalescing Brownian motion. Okay, I want to start with remind you guys about the Keyman's coalescing, which I'm sure most of you are already very familiar with. So Keyman's coalescing is just a system of particles where each pair of particles will coalesce into one particle with a constant rate independent of other pairs. So if you denote by capital NT the total number of the particles at time t, then NT is just a continuous time Markov chain, which jumps from n to n minus 1 with the rate n times n minus 1 over 2. So here, n times n minus 1 over 2 is just the number of your pairs if you have n population. So here is the illustration of the Keyman coalescing. It turns out that this Keyman coalescing has a very interesting property called the coming down from infinity. And it was pointed out by others in year 1999 that this process can enter from the infinity in the following sense. So he constructed a process capital NT on the with the positive t. So t here is strictly greater than 0, which evolves as a Keyman's coalescing. And if you take t goes down to 0, if you take a small time t, this capital NT, the total population will blow up. And moreover, he pointed out that the total population will be comparable to a constant over t. So Adams was able to construct this process by a graphical construction. So later, by Julian Bersticki and Nathaniel Bersticki and Leonid, they refined this result by showing that t times the this version of Keyman coalescing coming down from infinity, this value will converge to 2 almost surely, and also in LP for every p greater or equal to 1. They also point out that this version of Keyman coalescing with infinite many initial particles can be can be constructed as an increasing limit of a family of Keyman coalescing where you only have finite many initial particles n. So if you take n goes to infinity, this capital n here will converge to this version of Keyman coalescing, which comes down from infinity. So they were able to do that. They were able to do this by using the partition of the integers. And I also want to mention that in this paper, they actually consider a much larger class of coalescing process, which is the lambda coalescing. And you can also think about a model which is a Keyman coalescing incorporating with random movement of the particle. And the name of the model is called the spatial Keyman coalescing. And this model is a system of particles living on a given graph G. And you have two mechanisms happen simultaneously. So at each side, at each vertex of your graph G, the particles on that side will just coalesce according to the Keyman coalescing. And simultaneously, every particle are allowed to move as an independent random walk on your graph, well, independent of how particles are coalescing with each other. So if you denote by capital NTV by the number of particles at a given site y and at a given time t, then you can verify that capital NT is the Markov process. And similarly, you can construct a sequence of spatial Keyman coalescing in one probability space where you have n initial particles located at a root site. And if you take this n goes to infinity, this sequence of spatial Keyman coalescing will have an increasing limit denoted by capital NT infinity here. And this capital NT infinity can be considered as a spatial Keyman coalescing with infinitely many initial particles, all located at the root site. And let us also denote by NTG the total population of this process, the total population. Okay, again, here is an illustration of the spatial Keyman coalescing. You have two different mechanisms. The particle can do a random walk on your graph, and the particles on one side will coalesce with each other according to Keyman's coalescing. So in year 2006, Limik and Strom, they proved that if your graph G is a finite graph, then the total population will come down from infinity in the sense that for any positive time t, the total population is finite almost surely. And later, by Andrew and Bersticki, Nathaniel Bersticki and Limik, they proved that if your underlying graph is infinite, and of course it should be connected to the infinite graph, and they also have a technical condition with bounded degree, then actually your total population do not come down from infinity. It will stay as the infinite manifold particle forever. Okay, so for this talk, we want to ask if that's possible to consider this type of problem of Keyman coalescing with spatial movement in a continuum spatial setting, in the sense that I wanted my particle to do a Brownian motion instead of simply the random walk. So you might have different way to think of this problem, but we just gonna try to give an answer by using this duality type of argument. So it turns out that your Keyman coalescing process is a due process to the Wright-Fisher diffusion. So here the Wright-Fisher diffusion xt is just defined as the solution of a stochastic differential equation, which reads like this. So it is dxt equals to the square root of xt times 1 minus xt times dbt. Here bt is a Brownian motion. So if you have a Keyman coalescing nt and you have a Wright-Fisher diffusion xt, it turns out that the generating function of your Keyman coalescing can be represented by the moments of your Wright-Fisher diffusion. So this equality here is a duality relation between these two models. Okay, so it turns out that this duality actually have a spatial version, has a continuum spatial version, which is established by Shiga in 1988. And Shiga, he considered a random field UTX. Here, the UTX is just a solution to a stochastic heat equation, which looks like this. So this is a heat equation plus a noise term. So this noise term is is a certain type of a Wright-Fisher type noise. So it reads like the square root of u times 1 minus u times space-time white noise here. So here the space will be one dimension. So Shiga says that if you have a solution to this SPDE, then you can also construct a certain particle system so that the generating function of your particle system, this is like a multi-dimensional version of the generating function of your particle system, can be represented by your movements, again, multi-dimensional movements of your solution of the SPDE. So the system of particle is defined like this. It is a system of a Brownian particle in the sense that your particle are doing Brownian motions and their movement are independent with each other. And whenever each pair of particles, okay, so here, and with an additional mechanism that each pair of the particles will coalesce into one particle with a constant rate, but not according to the natural time, but according to their intersection local time. So I will be precise about this later. The point here is that Shiga constructed a point process, which is a due process to this SPDE here. And since this SPDE is a natural spatial analogy of our Rad-Fisher diffusion, we think this model particle system here is a natural analogy of a Kinman coalescing in the continuum spatial setting. So from now on, I will call this model the soft coalescing Brownian motions. So here is an illustration for a soft coalescing Brownian motion. Say you have two particles, whenever those two particles meets together, their intersection local time will accumulate. And until this intersection local time reaches to a value of exponential time, these two particles will become one particle. And this will always happen when the two particles are at the same position. And it will be helpful if you think that one of the particles survived and one of the particles died because of this kind of competition. Now, after we introduce the model, we want to ask if that's possible to initiate our soft coalescing Brownian motions with infinitely many initial particles. And the answer is yes, and you might actually have like multiple ways to define a process which is this model with infinite many initial particles. But what I want to do is I want to introduce the construction by tribe, which is very direct construction of this model. And this construction was in his paper in year 1995. The tribe defines a sequence of process, ATN, where for each and DT will just be a soft coalescing Brownian motion with n many initial particles. And then after you take n goes to infinity, this point process will have a increasing limit, which will be denoted by DT, and will be our soft coalescing Brownian motion with infinitely many initial particles. So the construction actually goes like this. You want so see if you want to construct a model with initial particles located at location as xi. So xi will be the initial location of the particle I. What you want to do is you want to construct a sequence of independent Brownian motions where the ith Brownian motion will initiate from xi. And you also want a sequence of independent exponential random variable, to control your coalescing time. And we will denote by Lig the local time between the particle I and particle J, which is simply the local time of the local time at the position 0 of the difference of the Brownian particle Bi minus Bg. Okay, so after you have all those three objects, you can define the lifetime for each of your particles by this induction. So the lifetime of the particle I will be denoted by theta I here. So theta I will be defined as the first time this process reaches to an independent exponential random variable. And this process is simply the summation of the intersection local time between the particle I and all the particle J, whose labor J is smaller than I. Okay, So you can use this formula and to define the lifetime for each of your particle inductively. So allow me to give you a graphical illustration of this construction so that it will be more clear. I'll see if at the beginning you only have one particle and this particle will just move as a free Brownian motion. And now if you initiate the process with two particles, you just need to, like I said before, you just need to kill the second particle when their intersection local time reaches to an exponential random variable. Now what you want to do is you want to add a third particle, and what you do is that you will kill the third particle when the sum of the local time of the third particle with the intersection local time between the third particle and with the first and both first and the second particle reaches to a exponential random variable. Then at this point, you will kill the third particle. And you can do this again and again. You will have more and more particles in the system, and then you will have an increasing limit of your point process. Then you define the limit as your soft coalescing Brownian motion with infinite many initial particles. So in this picture here, all the particles are initiated at the origin. Okay, after we have a nice definition of the model, we want to ask if that's possible that the soft coalescing Brownian motion also have the property of coming down from infinity. So it turns out that this question was partially answered by Hobson and Tribe in their paper in 2005. And what they did is they considered a soft coalescing Brownian motion, but not on the real line. This time, in their paper, they considered this model on a compact circle S, one-dimensional circle S. And also they assumed that their initial particles are sampled as the IID in an IID way uniformly on your circle. And they proved that the total number of your particle at time t, which is denoted by ZTS, is finite for any strictly positive time t. And they also proved that the rate of coming down from infinity is that it's like this. So it's the same as the Kieman coalescent. So in other words, the total population is comparable to 2 over t when you send t to 0. But what we are interested in is the soft coalescing Brownian motion on the real line, but not on this compact space S. So we want to ask the same question, but this time on the real line. So here is our main result. This is an ongoing work with Clayton Barnes and our advisor Leonid Mytnik. And we considered a soft coalescing Brownian motion on the real line, so this time. And we also allowing our initial particles to take any arbitrary position. So xi will be an arbitrary sequence on R. And we proved the following result. So not only we considered the total population, we considered the population that was in that is located in open interval U. So we will assume that our U is an arbitrary open interval. So if the intersection of this interval U with your initial location xi is bounded, then we can prove that almost surely for any positive t, the number of particles in this region at time t will be finite. And conversely, if this is unbounded, then the number of particles in this region will stay for as infinite forever. So this is our main result. And then we ask, of course, you can take this U, this arbitrary open interval as the whole real line R. Then what you're doing is you are considering the total population. So our result says that if your initial particles are located in a bounded set, then the total population will come down from infinity. And otherwise, if the initial particles are cannot be located in a bounded set, then the total population will stay infinite forever. Okay. Then we asked the question, what is the rate of this coming down from infinity for the soft coalescing bound motion? Well, in the case when it comes down from infinity. So it turns out in order to answer this question, we want to introduce a PDE here, a nonlinear PDE, a solution of a nonlinear PDE, which is simply a heat equation with a quadratic nonlinear term here, with a quadratic absorption. So this PDE will be a one-dimensional PDE, and it was proved by Legal in year 1996 that for any closed set lambda here, and for any random measure mu on the complement of this set lambda, you can always find a unique non-negative solution way to this nonlinear PDE here, where on the set lambda, the initial value of your PDE will be singular, will take infinite value, and on the on the complement of lambda, the initial value of your PDE will be this measure mu here. Okay, so actually V is a solution with this PDE with an initial value which is a mixture of a singular value and a measure value. So Legal was able to prove this by his famous model called the Brownian snake. Okay. So after, so with this V in hand, we are able to present our second result on the rate of coming down from infinity for our soft coalescing Brownian motion. So say dt is a soft coalescing Brownian motions, and we will define the set lambda be the singular points of the initial value of our coalescing Brownian motion, and we will define mu as the restriction of the initial value on the complement of lambda. So now you have a pair lambda mu, and by the way, this pair lambda mu is also known as the initial trace of the solution V. Okay, so now after you have this pair of lambda and mu, we have the following result. So let U be an arbitrary open interval. So again, we are thinking about the population in an arbitrary open interval. So if the intersection of U and your initial locations are bounded, then the number of particles in this region U at time t will have finite first moment. Well, here you need the t will be strictly greater than 0. And furthermore, if the closure of U intersect with our set lambda of singular points is empty, then actually you can prove that the number of particles will not blow up if you send the time t to 0.
Zhenyao?
Yeah.
Sorry, can I ask just a stupid question? I mean, when you say the xi set of xi intersection U is bounded, do you mean that there is a finite number of points in U, or that this is a bounded set in R?
Yeah, it's so this set is contained in a compact set. Okay. So it doesn't mean it has finite many elements. You can have infinite many elements. But
okay, thanks.
Okay, cool. Okay. So if lambda intersect the closure of U is empty, then you actually do not have blow up of the population. But if the lambda intersect with the closure of U is not empty, then you do have, if you send time t goes to 0, the population goes to infinity. And we can also show that your population is comparable to the integration of the solution V, which I introduced earlier, on this region U. Okay, in the sense of L1. So basically you can identify the rate of flow coming down from infinity. Okay, so this is our second result. And you can, of course, take your the U as the whole line R to consider the total population. So our result on the total population is like this. If the initial particles are unbounded, so if this set here is unbounded set, then you always have infinite many particles. But if your initial particles, location of your initial particles is bounded, then at any positive time, the total population have finite movement, and the total population is comparable to the integral of a solution to a nonlinear PDE in the sense of L1. Okay, so now after we have presented our result on the rate of coming down from infinity, you can see that the rate is represented by an abstract integral of a solution of a PDE. So it is not really clear how fast, how exactly the rate of coming down from infinity is. So here we have two examples. So in one example, every initial particles are located at the origin. So xi equals to 0 for every I. So at the origin, you have infinite many particles. So in this case, we showed that the total population is comparable to a constant over square root of t. And here's another example. So you can also think that the initial particles is a dense subset of a compact set, compact interval 0, 1. And in this case, you can show that actually the total population is comparable to 2 over t. So this second example is actually a parallel result of the hops and the tribes result in on the circle of on the compact set case. And I want to point out that the rate of coming down from infinity are really changing if you change the initial configuration of your model. So now at least we have two examples here. One is the 1 over square root t, one is the 1 over t. So we think it's natural to ask if that's possible to have the total population ZTR to behave like t to the minus alpha, where your alpha are actually between 1/2 and 1. So we ask this question for any alpha between 1 over 2 and 1, is that possible to find an initial configuration so that your total population behaves like t to the minus alpha. So it turns out this question is related to the fractal structure of the set lambda. So lambda is our singular set of the initial particles. So let me just give you a quick review of the notation here. So if you have a set A in a subset of R, and we denote by AR the R neighborhood of our set A, and we say the set A has the Minkowski dimension delta if the Lebesgue measure of R neighborhood of A, a log of this Lebesgue measure over log of R will converge to delta when R goes to 0. And when a set A has a Minkowski dimension delta, we see it is a Minkowski measurable with a constant kappa if the Lebesgue measure of the R neighborhood of A over R to the 1 minus delta actually converges to this kappa when R goes to 0. So here is just the some definition of some classical concept of fractal geometry. So here, let me present our final, the last result. If our initial particles is bounded, so in this case, the total population will come down from infinity. And let us also assume that there's no isolated point in the sense that the set mu will be 0. So every point is in the singular set lambda. And we also assume that the lambda, the singular point, has Minkowski dimension delta. Then we can show that the log of the total population over log of t will converge to the minus 1 plus delta over 2 in the sense of probability. So here the minus 1 plus delta over 2 is actually the rate of coming down from infinity. But what we really want to prove here is the following statement here. But for the moment, there's still some problem in this in our argument. So I'm not sure it may or may not show up in our final paper. So I list this as a conjecture. It says that if your lambda is, if you first assume that the lambda has a Minkowski constant kappa, then we want to show that the dt, the total population is comparable to the constant over t to the power 1 plus delta over 2. So allow me to give you a very quick review for how we can prove this all those results. Again, what we considered a model called the soft coalescing Brownian motion, and we proved that its rate of coming down from infinity can be described by a certain nonlinear PDE with a quadratic nonlinear term, allowing a singular initial value or a measured initial values. And we were able to make a connection between these two mathematical objects using a duality type of argument. So we make a connection by this chain here. So on one hand, the soft coalescing Brownian motion is as I mentioned before, it's a dual process of this reaction-diffusion equation here, a stochastic reaction-diffusion equation with Red-Fisher type noise. And this is established by Shiga in the year 1988. And this duality is also known as Shiga's duality. And on the other hand, our nonlinear PDE here can be represented, has a probabilistic representation using Legault's Brownian snake. So this is established by Legault in 1996. And I think I mentioned it before. So this Brownian snakes is actually introduced by Legault to study the genealogical structure of certain measure valued process, which is known as the super Brownian motion. And I think yesterday, people already mentioned this model here. So the connection is holds for the critical one-dimensional super Brownian motion. And it also turns out this super Brownian motion, if one considers its density, then the Kahn and the Shiga, and both Kahn and Shiga and the Reimers, they proved independently that the density of this measure value process can be represented by a certain type of stochastic reaction-diffusion equation with a Feller type of noise. So here the noise is square root of u. And above we have the Red-Fisher type, which is square root of u times 1 minus u. So you can tell that these two equations are quite similar to each other. So what we did is that we argued that these two, the solution to these two different equations shares a lot of similar properties. And by doing that, we can kind of build a chain from this model to this model and to help us to prove our final result. Okay, so here you have it. Here you have the branching system of several complicated branching process. And on this corner, you have the reaction-diffusion equation. And also with those two, we can prove something for our population model. And thank you. And I want to end this talk by mentioning that this is based on my joint ongoing work with Clayton Barnes, which is who is a postdoc at Atelier, and our common advisor, Leonid Mytnik. Thank you very much.
Great, thank you very much for a very nice talk. Are there any questions in the audience? Julien was first.
I may have missed something, but I was a bit confused at some point because so you have results about the speed of coming down from infinity, but one of the first results you showed, I thought meant that there was no coming down from infinity. You had a result which says that if you have a set U such that the number of particles in U is infinite, then it stays infinite forever. For the soft.
Okay, it's here then. Let's just take U as the real whole line here. So the statement says that if the location of the initial particles, if the set of the location of the initial particles is unbounded, so for example, if you have one particle at each of the integers position, then the total population of your if you consider the total population at time t, it will be infinite.
Okay.
Yeah, almost surely. So this is the statement.
But isn't this the one where you then have, so you take U equal R later, and you have that is decreased like root T, one over root T, or that root T?
Okay.
So how do you?
For in these two examples, in the first example, all the initial particles are located at one point, so it's bounded. And in the second example, the initial particles, their location forms a dense subset of a compact interval that are 1. So in this case, this set is also bounded.
Okay,
so also this example is.
Okay, I had missed the detail. Thanks. Okay.
Yeah. So do you think that the soft coalescing Brownian motions would still come down from infinity if you added a branching mechanism?
Good question. So I think so. I think well, someone need to prove it, of course, but I think for most of the branching mechanism, you will have this coming down from infinity, but someone need to prove it, of course.
Thanks. Are there any questions online? Maybe last one. Oh, there are some more questions. Sorry. Please. Do you have a microphone? There's some in the room. Could you pass it to the back? Thank you.
Hi, Zhenyao. Can you? So here, in your result, the rate of coming down from infinity depends on the initial configuration, right?
Yes.
Could you say something about this? Could you explain why this is the case?
So actually, when we first got this result that if all the population are located at 0, then the rate is 1 over square root of 2, square root of t. We are also kind of surprised by this result. And that's why later on we considered by this further question. It turns out it's related to this lambda here. So it's the rate of coming down from is closely related to this lambda. I think it depends on how the local time behaves. If you have two particles, they are located together at the beginning, then they will have a local time which grows like square root of t. I don't know if that makes sense to you, but if you have two particles separate from each other, there's intersection local time where not grows. I don't know if that makes sense to you, but yeah, of course, we just started thinking about this problem for like half a year, and there are still a lot of intuition. Even myself, I'm not really quite understand yet. So
yes, do your results about coming down from infinity? Can you then say anything about solutions to that spatial Wright-Fisher stochastic PDE? Is there an interpretation there?
Oh, okay. So our result is closely related to the property of this SPD, of course, because as I mentioned, we used the duality to prove our result. So our result actually related to the asymptotic of this solution U when the initial value of U0 goes down to 0. So if you take the initial value U as a very small initial value, then if you can describe how fast, of course, if the initial value if the initial value goes to 0, your solution will also goes to 0. But if you can describe how fast this is, then you can kind of reconstruct our result.
Something about the fixation probability as time's going to 0, or the rate?
I think it's kind of like the rate. I'm not sure what you mean, like fixation point with fixation time means. So I'm sorry about that.
Okay, never mind. Thank you.
Okay, maybe a quick last question from me then. You said there was a similarity between the two SPDs with Wright-Fisher noise and the fellow noise.
Yes, yes, yes.
Can you be more specific, or is it just sort of that they look similar for you close to 0? Or?
The similarity. So for this SPE here, so if you look at this noise term will be Holder, not Lipschitz, right? And it will only be Holder when U is 0 or 1. Like I mentioned, I really want to understand the solution when the initial value of U is very small. So when the initial value U is small, you can kind of imagine the solution U is also small. So when U is small, what is really playing a role here is the Holder continuity for this term when U equals to 0. So when U is small, you can kind of see the solution, they are actually very similar to each other. So by studying this solution when U is small, you can kind of get the result for the behavior of the solution of this SPV here when U is small.
I think there are no further questions online. So all right, let's thank Zhenyao again, please.